Okay, so this lecture will blow your mind because I'm now going to show you that renormalization group is not just some special thing to do with statistical mechanics and integrating out fluctuations and all of that. I'm going to show you that it has a much broader interpretation and significance, and can be applied in many other areas of physics other than just statistical mechanics. So last time what we did was we finished our renormalization group calculation from the epsilon expansion, showing you how you can compute anomalous dimensions by doing Feynman diagrams, which I didn't show you, but I referred you to the point in my book. I showed you the results. Oh, wait. I just remembered I need to make a correction because there was a typo in my notes. And before I get into that, I want to just correct that typo. So let me go right back and show you where the typo is. It was noticed in class, and the typo is right here. Right. So the typo occurs right here. Thank you. I'm correcting your typo. So the typo is here. So this bracket is a mistake, and it should be like that. That's what I couldn't see when the question was asked in the class. And so this goes here, and that goes there, and that answers the question that was raised during the lecture. So it was just a typo. I just copied it down wrong and couldn't see the mistake in my notes because I'm too close to them. All right, so let me go back to my introduction for today's lecture. So what we did was we did all this calculation, blah, blah, blah. We computed the renormalization group recursion relations. We found the fixed points. We saw that there's a new fixed point to order epsilon squared, the Wilson-Fisher fixed point. We computed that. We computed the linearized RG around it. We computed anomalous dimensions. We computed scaling laws, and we found that the critical exponents were shown here on the left-hand panel, and even just to this order in epsilon, just calculating to this order and then setting epsilon equals 1, which is completely unjustified mathematically, but can be improved, we saw that this already is starting to correct the discrepancy between mean field theory and what we see in experiment or computer simulation. And then at the end of last lecture, I went back to dimensional analysis. Now you'll remember in this course, the first thing we did in this course was I taught you dimensional analysis, okay? And then we did dimensional analysis on field theory, and I derived for you the mean field exponents by dimensional analysis. And then what I did yesterday, not yesterday, on Monday, what I did was I asked, how did we get anomalous dimensions in this renormalization group calculation with all these Feynman diagrams and blah, blah, blah. And I explained to you that what is happening is that we get a scale interference. And what we saw happening was shown here at the 2-point correlation function level, where you would expect on dimensional analysis grounds that the correlation function has dimensions of length squared. And so in terms of the wave number k, which has dimensions of inverse length, has to scale like k to the minus 2. And the only way that it could scale as k to the minus 2 plus eta, which is what experiment, what simulation, what renormalization group tells you, the only way that can happen is if there's another length scale that comes into the problem and restores the result of dimensional analysis. And there's only one length scale left. And that length scale is the lattice scale, the microscopic scale. So you've got the absolutely preposterous situation. You have never seen this before in your physics career as a student, that you have a length scale which is, say, the radius of the galaxy, and a length scale which is of order the atomic scale, and both of them need to be taken into account in order to do the calculation and get the correct answer. So this unreasonable dependence on the microscopic scale, when the large scale structure, the infrared structure of the theory is on many, many scales greater than that, that's called scale interference. And it comes down to what we talked about at the beginning of the class, when we did dimensional analysis, and then we did intermediate asymptotics of the second kind. Remember, we did type 2 asymptotics, where you can take the limit of a dimensionless group going to 0, but you cannot neglect it in the asymptotics because there's a singular dependence on that. And I told you that is what is happening here in phase transition problem, and that's indeed what we saw with this explicit formula in the middle of the page. This explicit formula here, where if you compute the 2-point correlation function, you find that it has a singular dependence on the lattice scale. And that was the reason that it restores dimensional analysis, because a to the eta times k to the eta is just a dimensionless number. So it restores dimensional analysis, but eta now can be any exponent you like, and then you can calculate that, and it turns out not to depend on the lattice scale. And so that's what we learned last time, and that is the punchline of this course. Okay, did I make a mistake?
No, I was just curious why you said it's a singular dependence, because the function is still analytic.
If the function is going like, say, a to the 0.3, blah, 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 that's not analytic. It doesn't have a power series expansion. It's not analytic. It doesn't have a power series expansion. I can't write it as an analytic function.
Ah, okay, because eta is not an.
Yeah, yep, exactly. All right. So now, so all of this in the end, even though we did all these calculations and we talked about block spins and scale invariance and all this stuff, in the end, it boiled down to a problem of asymptotics. So today we're going to look at renormalization group for differential equations. And we're going to see that even though we have no statistical mechanics, we have no fluctuations, we have no partition function, we could be far from equilibrium, you can still get anomalous scaling laws and use a normalization group. So I think the easiest way for me to do that is to make this just big like that. And does it work for you guys? Yep. And so you won't get to see the previous page. Okay, so this is a lecture that I gave at some mathematics conference. I don't remember when it was, maybe some years ago. So I'm going to go through this to make it so it's a lot quicker. And let me just make a color here for my pen. So if I want to outline anything, I can go ahead and do that. So here's a summary of the lecture. So as you know, renormalization group were originally developed by physicists attempting to understand divergent terms in perturbation theory and the short distance behavior of quantum electrodynamics. That's what Feynman, Tomonaga, and Schwinger won the Nobel Prize for in the middle 1960s for their work that they did in the 1940s. And then Wilson won the Nobel Prize for his work, developing it even further along the lines that we have presented in this course. And all of those, and as we know that what the normalization group, the problem it solved was, first of all, the problem of why you get critical exponents in phase transitions and so on. But it also led us to think about effective theories, and led us to think about theories at different scales of description, different levels of description, which is what we talked about, starting with Leo Kadanoff and so on. So now I'm going to show you that the same thing happens in many examples in physics. I'm going to talk about one here primarily, which is a problem like the flow of a fluid in a porous media, but it also happens in the propagation of turbulence. It happens in problems in ecology, and this is work that was my original work in the late 80s and early 1990s, in collaboration with Yoshi Ono and students Lin-Wan Chen, John Vasey, and postdoc Olivier Martin. So this is all work that you won't find in any textbook except mine. Okay. So we're going to talk about differential equations, not field theories. Nothing is stochastic, and we don't even have scale invariance. Although the one example I'm going to show you actually does have scale invariance. So here's a kind of overview of what one can do. So I'm going to talk about self-similarity and nonlinear partial differential equations. I'm going to give you an example of that, and we will work through it. But once we did this work, then we discovered that we can apply this to looking at all sorts of problems in applied mathematics where you have singular perturbations, where you have non-analytic behavior as you have some small parameter. And this is a classic problem that goes right back to the dawn of fluid mechanics, to Stokes, who wrote down the Navier-Stokes equations and then said, okay, let's do the simplest problem. Let's look at the flow of a laminar fluid, never mind turbulence, a laminar fluid past a sphere, or take honey, put your finger in it and look at the flow of the honey as it goes past your finger. Okay, you would think that this problem is like, well, this is trivial. It was written down in 1850. It should be a very simple problem. Turns out that problem was not solved for over 100 years, and in order to solve it, you had to create a new branch of applied mathematics called singular perturbation theory. And even singular perturbation theory, to solve that problem, the solutions don't work terribly well. And you can do better by using a renormalization group. So these problems are absolutely fundamental. And I could give a course on applied mathematics just on perturbation theory, and my course would be, take a textbook like Bender and Orszag, which is the best textbook in applied mathematics I know. Take that textbook and do every problem in that book, not by the way that is described in the book, but by using the normalization group. And we did that. We wrote a paper in 1996, which does exactly that. Okay, and then one of the other reasons why this is super cool is that this is a way to improve numerical methods for solving differential equations. And in fact, in work that I'm doing now, I think that these are methods that could potentially be used to improve machine learning and neural networks and so on. So I'm not going to do that today, but okay, so why do I want to look at renormalization group for partial differential equations? So here's a quote from Richard Feynman in the Feynman Lectures on Physics, Volume 2. And he, excuse me, after his chapter on electricity and magnetism, he talks about Navier-Stokes equations. He writes down the equations. And this is what he says: we've written the equations of water flow. From experiment, we find a set of concepts and approximations to use to discuss the solutions, vortex streets, turbulent wakes, boundary layers. When we have similar equations in a less familiar situation, and one for which we cannot yet experiment, we try to solve the equations in a primitive, halting, and confused way to try to determine what new qualitative features may come out, or what new qualitative forms are a consequence of the equations. The example I just gave you of Stokes trying to solve the flow around a sphere or a cylinder, where you write down these equations, and my goodness, they're incredibly difficult to solve. They have all sorts of solutions that create emergent structures like Kalman vortex streets and things like this, if you know what those are. I'll show you some examples in a minute. All of these things come out of these equations. Feynman says, our equations for the sun, for example, as a ball of hydrogen gas, describe a sun without sunspots, without the rice grain structure of the surface, without prominences, without coronas. Yet all of these are really in the equations. We just haven't found the way to get them out. And then he says, the next great era of awakening of human intellect may well produce a method of understanding the qualitative content of equations, qualitative content. So this is what a statistical mechanic would call the phase diagram. So if I give you a differential equation like Navier-Stokes equations with boundary conditions and so on, I want to know the phase diagram of it. As I change a control parameter, such as the Reynolds number or the Prandtl number or whatever it might be, what new emergent structures come out, and then what are the quantitative descriptions of those things? That's what Feynman was looking for. So, and when he wrote this, you couldn't do it. Today, we can do it a little bit, but still, it's not great. So here's an example. This is an example that he talked about. He mentioned here, he talks about we cannot see the water equations contain such things as the barber pole structure of turbulence that one sees between rotating cylinders. So here are rotating cylinders. You have an inner cylinder and an outer cylinder. The cylinders can rotate with respect to each other. The outer one is made out of glass or something, so you can see through it. And you can see that the fluid, instead of just going round as like a rigid body, actually develops these vortices that you can see here. There's a whole sequence of them here. These are vortices in the transverse direction, and they actually can wave and wiggle around like that, and eventually they can become turbulent as you increase the rotation rate. So that's an example of different phases of fluid matter in what's called a Taylor-Corrett apparatus. Now you might say, well, how complicated can the phase diagram be of such a system? Well, here's the phase diagram. Okay, right, everybody in the room falls over. Right, it's amazingly complicated. This is the outer cylinder on the horizontal axis, the inner cylinder rotation rate on the vertical axis. And this, you have all these different phases. And one of the things that we discovered actually in this system here is as you go further in this direction, okay, as you go further in this direction, what happens is the fluid becomes correct flow means rotating like a regular body. What happens here is that you actually get a transition to turbulence, and that transition to turbulence we now know from theoretical work that we did and experimental work our collaborators did, that transition to turbulence, even though it's governed by the Navier-Stokes equations, is a non-equilibrium phase transition in the universality class of directed percolation. It actually looks like a statistical phase transition for a system that is out of equilibrium. And we know this because we can measure the critical exponents. We understand mathematically why this happens. Okay, so now I want to tell you about renormalization group methods that for differential equations. So this is an overview of all the things that we did, and I'm not going to go into all of this here. But what I am going to talk about for you right now is I'm literally going to show you essentially this part over here. So we're going to talk about that, and I'm going to show you mathematically how one can use a renormalization group in differential equations, and to see that you can get anomalous scaling laws that violate dimensional analysis and mean field theory. This work had its foundation in this book by a Russian mathematician, applied mathematician, Grisha Barenblatt. And I found this book by accident one day when I was browsing in the library at the University of Illinois at Urbana-Champaign. Now, in the days before you had Google Scholar and things like this, here's what you would do. If you found a reference in a paper, you'd then go to a book or something like that. You'd go and find it in your library. We had a very good library at the University of Illinois, and you'd go and find it, and there you get the book. And because books in libraries are ordered by topic, what I would do is whenever I had to go to a place in the library, my theory was that there were other things in the library geographically near where I was, which were relevant to the science that I wanted to do. So I would then just pull books off the shelves at random and then flick through them to see what I could find. Okay, so I found this book this way. And I also found another thing this way. I was working at the time as a postdoc. I was working on how patterns form in nature. I was working literally on how snowflakes grow and how to predict the speed of snowflakes. And it turned out the problem of predicting the speed of snowflakes turned out to be a very singular problem that required very strange asymptotics. And that's how I started thinking about renormalization group. And in fact, I discovered that there was an analogy between the problem of how snowflakes grow and the problem of how bubbles grow in a very viscous fluid, or a fluid between two glass plates. And so that was another important discovery that I made that then propelled the field of pattern formation forward in my work and the work of other people in the field. Okay, so the basic phenomena was discussed in Barenblatt's book, but they didn't know where it came from. Then I solved this problem with my collaborators, and we wrote papers on it, and I wrote it into my textbook. And actually, Barenblatt made a second version of this book. This book was originally written in the 1970s, 1979. Then after the Soviet Union fell, in the early 1990s, Barenblatt was allowed to leave and moved to Cambridge in England and was the G.I. Taylor Professor of Fluid Mechanics at Cambridge. And we became very close friends. And he actually ended up making a second edition of this book and put in a whole section on the normalization group and mentioned our work in the introduction as the thing that has motivated all of that. Okay, so what did we do? I'm going to talk about similarity solutions of differential equations, which you've learned about on your mother's knee, but you may not have thought about them in quite the way that I'm going to tell you now. So let's suppose I've got a problem, which is a partial differential equation for a field U in space x and time t. And a similarity solution is a solution that has the functional form shown at the top here. This is it has a scale symmetry, and the process of time evolution is analogous to the process of rescaling a space. So this is called a similarity solution. Another way you can have a similarity solution is what's called a traveling wave. So here is a traveling wave, and you've seen those before. That is also a particular symmetry of the solution. Why? Because I started off with a function of two variables. And that's on the left-hand side. And these things here are functions of one variable. Right? So it's a function of x over t to the beta. It's a function of x minus vt. And this function of one variable, this is exactly analogous to the data collapse scaling. That Widom and Kadanoff had figured out in the middle 1960s, in 1965, and was the basis for Kadanoff to develop the Kadanoff block spin construction to explain how that happened in phase transitions. But you don't need a phase transition to see this. You can see this just in a regular differential equation. And so what we want to do is we want to understand in these sorts of problems the critical exponents, alpha and beta, or in the particular case of the traveling wave, the velocity v. And you can see that the v is like a critical exponent, because if I take a traveling wave and now I make a change of variables between x and t, as shown up here, then I can transform a traveling wave into a similarity solution, and the speed of the wave turns out to be a critical exponent. Okay, and in fact, what I was working on was the problem of how fast a snowflake grows. Turns out to be a fantastic problem. You'd never think you'd learn anything fundamental about physics from that, but you do. And the speed of the snowflake growth turns out to be like a critical exponent. Okay, so let's talk about dimensional analysis, and let's talk about the simplest equation that we can think of, which is the diffusion equation, which you learned on your mother's knee. So here is the diffusion equation. We're going to solve this diffusion equation here with an initial distribution that has a width L, as shown over here. And when I wrote these slides, I did something that I wouldn't do today. I left out in here a diffusion coefficient called kappa, which has dimensions, the right dimensions of the diffusion coefficient, to make sure this thing is dimensionless. So that is missing from here. It doesn't matter, but I want you to pay attention to that, because we'll introduce that later. So wherever there really is a kappa in here as well. So wherever you see t, it's basically t is like kappa times t. Kappa is a diffusion coefficient. Okay, so I can look at my initial condition, and I have an area under the curve, which I'm going to call the mass, and we'll say it's a Gaussian. And now we can ask, what happens when I evolve it forward in time? When I evolve it forward in time, you can all solve this problem. It's like solving the Schrödinger equation for a free particle. What you get is the solution you can see on the screen in the middle of the page. It's still a Gaussian, but now the width of it has increased. Its width was initially L squared, but now its width is L squared plus kappa times t. Okay, So now let's have a look at the long time behavior of this solution. So if I keep t, I send t goes to infinity and L is fixed, then my long time behavior looks like this. Okay, so that just says I start off with some initial condition, along times it diffuses, it stays as a Gaussian, just as you know is a solution of the diffusion equation. But I could equally well do something different. I could say, let's keep t fixed, choose a time, 5 seconds or something, and then make the width of the initial condition go to 0, and then I get the same result. And so because I get the same result, what we've learned is that the asymptotic behavior of the initial value problem is given by the similarity solution. And the similarity solution is the solution that corresponds to L going to 0, which means that if I take a Gaussian and take L goes to 0 of a Gaussian, that just goes to a delta function. So the solution from a delta function, initial condition, actually controls the long time behavior of this differential equation. And so that's why finding similarity solutions, the similarity solution well, I've taken the initial condition width to 0, that creates an initial distribution, which is a delta function, and then finding what is the solution that corresponds to that, that then tells me in many classes of problems that this is a dynamical attractor for the behavior of the system. Okay, so now let's think about dimensional analysis. So in dimensional analysis, we know how to do that. You write down your dimensionless groups, and then you try, as I've shown you over here. We did this early in the course, and you might have some other dimensionless group which is very small, such as the size of the system divided by the radius of the moon, let's say. And so you say, well, that's equal to 0, so I can just ignore it. So let's have a look at the diffusion equation. So in the diffusion equation, I can write down the following 3 dimensionless groups. So first of all, there's x over the square root of kappa t. So you think of kappa being in there. I've got another length scale, which is the length of the width of the initial condition, that's L. So I can also write down pi 0, L over the square root of kappa t. And then lastly, if I take u over the mass of the initial condition times the square root of kappa t, that is also dimensionless. And so I can write down that pi is a function of pi 0 and pi 1. Pi 0 is this one over here, pi 1 is this one over here. And now as I take the long time behavior of the system, so in the long time behavior, pi 0 goes to 0. Because L stays fixed, kappa t is going to infinity, and so so pi 0 goes to 0, so we just ignore pi 0, and then we get that u is just m over the square root of kappa t times a function of the square root of t, as pi 0 goes to 0. That's the long time behavior. And then if I want to know what that function f is, all I do is take this form, substitute it into the original partial differential equation, and then I get an ordinary differential equation for f. So if I substitute this into the diffusion equation, what that does is gives me an ODE for f, and that ODE is easily solved. It's just and the solution is e to the minus x squared. So that's how you can get the solution that we talked about over here. Okay, so that's the diffusion equation, and what we talked about at the beginning of the course was that there are many examples in physics where we have this case 1 asymptotics, common sense asymptotics, but we also talked about this one, case 2 asymptotics, and where you have a singular dependence on pi 0 as pi 0 goes to 0, and it's singular because it's going with a form like this, pi 0 to the minus alpha. So if alpha is positive, then as pi 0 goes to 0, this thing goes to infinity. If alpha is negative, it goes to 0. So the only way to get a non-zero function is that there is some special balance between this pi naught outside and the pi naught inside, just as we saw with Widom scaling and Kadanoff scaling in phase transitions. And that's called type 2 asymptotics. That's what Barenblatt wrote about in his book, because he'd found examples of this, and it was like, what the heck is going on here? And they could solve those things numerically. Okay, so now we're going to do something different. We're now going to take the diffusion equation and I'm going to modify it in the following way. I'm going to say that the diffusion coefficient is a half, really a half kappa, when dx squared u is positive, and it's a half kappa times a number when dx squared u is negative. And I'm going to choose to write that number as 1 plus epsilon, because in fact, I'm going to do perturbation theory in epsilon. Okay, so this describes the pressure in the fluid passing through a porous medium which can expand and contract irreversibly. So it's a sponge. As the fluid goes through the sponge, it pushes the sponge pores apart. As the fluid goes out of the sponge, out of a pore, the thing contracts, but it can contract irreversibly because it can dissipate heat, or there can be some dissipation. And so the two processes are not the same. And so the diffusion coefficients in these two cases are different. Okay, so this irreversible behavior for a process too complicated to explain is the equation that we are left with. So let's have a look at what that means. So here is my my initial condition, or here is my condition, my solution at later times. In this part here, I've got the coefficient, which is a half kappa times 1 plus epsilon. And in this part over here, I have just a half kappa as my diffusion coefficient. So I have a different diffusion coefficient for different parts of the solution of this equation. Now, this equation, when you look at it, you might say, well, wow, that's a weird equation. How do I derive that? Well, you know how you derive the diffusion equation. The diffusion equation comes from a local continuity equation. You just say I've got local conservation of mass, and then you say the mass flows according to the gradient of the density, and then I get the diffusion equation, two-line derivation. But in this particular case, it's not derivable. Whoops, go back. It's not derivable from that. And because it's not derivable from that, what it tells you is that the mass of the distribution is not conserved. So the initial mass, the area under the curve, is not the same as the area under the curve at a later time, because the equation does not come from a local conservation. Okay, so now we have the question: what is the long time behavior of the equation, which I'm calling the Baron-Blatt equation? So you might say, well, it's easy. We can figure out this by using the principles of dimensional analysis. What does dimensional analysis tell us? Well, what we've done is we've added one more dimensionless group. So we have a pi 3. Actually, what did we have before? We had pi 0 and pi 1. So we've got so for this equation, what we have is a pi 2, and that pi 2 is this dimensionless parameter epsilon. So you might say, well, I've just added one more dimensionless parameter, so then what I should expect is that I have the same behavior as before, but now this scaling function now perhaps depends on epsilon rather than just depending on x over the square root of kappa t. Okay, so that's what you would think. Okay, well, it's easy to check. We do exactly what I told you. You assume it's true. You substitute it in to the partial differential equation, into Baron-Blatt's equation. So here's your solution. I've got over here, I've got one diffusion coefficient in the green. I've got another diffusion coefficient in the red. So in those two different separate regions, I get two separate ordinary differential equations, one with a diffusion coefficient of a half, 1 plus epsilon, one with a diffusion coefficient of half. And then I want to match those derivatives at this boundary over here so that the solution is continuous and has continuous first order derivatives. And what you find, I'm not going to go through and show you this, when you take those equations, you can easily prove that it's impossible to do that. You cannot find a solution that is smooth and matches all the derivatives at this boundary between these two different regions. Okay, so you say, okay, well, this equation came out of somebody's back pocket. Maybe it's complete nonsense. So maybe it doesn't even have solutions. Maybe it's not a well-posed problem. But you can prove rigorously that there exists a unique solution of this initial value problem with continuous second derivatives. So the thing is that this is not solution. And I'm going to show you now that the solution looks like this. It looks like 1 over t to the 1/2 plus alpha. Now alpha will depend on epsilon, then times a scaling function of x over the square root of kappa t, and then epsilon. And so in this problem, what you have is an anomalous dimension. And that's what makes this problem so complicated. Okay, so how do we get this result? I'm going to show you a heuristic derivation, which will take 5 minutes. And then I'm going to show you, so this is a 5-line argument, which is really, really useful for these sorts of problems. And then I'm going to show you how to do it using field theoretic renormalization group. Okay, so we know that the mass of the distribution is not conserved. So what you might say is the following. Let's suppose that epsilon is very small. Then you would expect that the mass of the distribution, the area under the curve, is not going to be conserved, but maybe it's not going to be the conservation law is not going to be broken too quickly. So think about it like this. As this thing is diffusing out, some of the stuff that is diffusing is sort of disappearing into thin air, and we can't see it. So let's say, what if the rate at which it disappears into thin air is going very slowly compared to the rate at which it expands? So we're going to make an adiabatic approximation. So we're going to say that the removal of mass occurs slowly. So you're going to say, think of it like this. The fluid expands out, some of it gets lost, a little bit gets lost, but very slowly. And so the solution locally adjusts to the Gaussian profile that we know is the normal case for the regular diffusion equation. Then it diffuses out a little bit of mass gets taken away from the solution of the differential equation, and then it adjusts to the Gaussian profile, and so on and so forth. So the removal of mass occurs slowly, and the distribution adiabatically adjusts to the Gaussian form above. So this is the solution that we wrote down for the regular diffusion equation, where there is no epsilon. But the only thing that's different here is we're now going to say that the mass of the distribution is no longer a constant, as it is for the diffusion coefficient, for the diffusion equation. It's actually a time-dependent variable. Okay, so we're going to look for solutions that have this form. Yes?
Do you think you could give a little bit more intuition about this equation before we? I feel like I'm still wrapping my head around having 2 different diffusion coefficients.
Right, I'm going to show you. I'm going to show you. Let's suppose, thanks for the question. So let's suppose I have a porous rock. Okay, and I have here an impermeable rock underneath it. And I have on this rock, I have a fluid that is like this. This is the fluid. Okay, it's a pile of fluid leaked out of my basement or something like this. Okay, so it's filled up the rock. There's gravity going down like this. And so what's going to happen is at later times, what is going to happen is that this this groundwater mound is going to settle under gravity, and my rock has still got these pores like this. Okay, so you understand the setting here. All right, now, as it has settled, so this is the time evolution, as it has settled, you can see that some of the pores at the top these pores over here, those pores have emptied, and these pores over here and over here, these pores have filled up. Do you see that? As this groundwater mound has spread. Now let's have a look at what happens when pores empty and fill up. So here is a pore in the rock. It starts off initially empty, and then it becomes full. And here is another pore, which is initially full, and this one becomes empty. And those two processes are the time reversal of each other, and everything is symmetric. Okay, if that were the case, then the equation governing this would be dH by dt, the height of this mound as a function of x, would be del squared of h squared. Okay, and you can derive that, and it's derived in my book. Okay, so that would be the solution. Okay, that would be the equation. Okay, now first of all, this equation is too hard to solve. You can solve it. I wrote papers on this, and so did Barenblatt. But for simplicity, I'm going to just say, fine, let's just cross out. Let's just ignore the power 2 and just replace the power 2 by 1. So that's the first thing, just to sort of as a toy model of this. Okay. The other thing, so that's step 1. The other thing is to notice that these processes here, this is not actually what physically happens. What physically happens is this. If I start off with a full pore, if I start off with an empty pore and it fills, it goes like that. If I start off with a filled pore and it empties, what happens is I get a thin wetting layer around the outside of the pore. So it doesn't actually empty all the way. I've got a thin wetting layer. And what that means is that the mass of the fluid, literally the fluid that is diffusing out as this groundwater expands, is now not being conserved, because it flows into pores, but when it flows out of them, it leaves some behind, but we don't know that it's done that because it's a thin wetting layer. And so the mass of the fluid has been left behind, and so it is not conserved. That's another physical realization of this. Did I answer your question?
So the filling would have the second derivative being positive.
Yes, because one is when the dH by dt is negative, and one is when dH by dt is positive. Right. Okay. So that's an example of this problem. This is more physical. The linear problem also occurs where it describes the pressure, but this is the easiest way to see how this can happen. Okay, now let's ignore all that. Let's have a look at what happens here when we try to solve the solution for this equation. So we've got the equation like this, and we're going to say this removal, like I've shown you here, this wetting layer is very, very small. So because of that, what we can do is we can say, right, we'll say that M is occurring slowly. So we're going to say that the distribution of which always adjusts to the Gaussian distribution, and there's only an M of t. So the only thing we don't know is what is the time dependence of M of t. Okay, so let's write down an equation for it. So the M of t is the integral of u from minus infinity to plus infinity. It's the mass of the distribution. So the time derivative of M of t is d by dt of u of x of t, and that is, and in the equation of motion, I'm going to write the Barenblatt equation as du by dt as some diffusion coefficient times u, and the diffusion coefficient has a spatial structure, so we're going to write it like this. Now, what is that spatial structure of d of x? Well, we know this solution, it looks like this, and then we know from the way we set up the problem that therefore to the left of this line, the diffusion coefficient has one value, and to the right of it, it has a different value, and it differs by epsilon over 2. And so this diffusion coefficient has a discontinuity in space at this boundary. And where is this boundary? Well, this boundary is diffusing out, and so the position of the boundary is determined, at least to order epsilon, by this equation here. So if that's the equation of motion, then I can do this integral by parts. So if I do it by integration by parts, then I simply get the term over here by integrating by parts. And because the d as a function of space is a step function, when I take its derivative, I get a delta function. And so what I end up with is dm by dt is epsilon du by dx evaluated at this moving boundary. Okay, now all I have to do is then take my solution. I know what u is and stick it into here. And then what I get is an equation for m. So there's my equation for m, and I can solve that equation exactly. And the solution to that equation is this. M of t is m of naught times L to the power 2 alpha over T, kappa T plus L squared to the power alpha, where alpha you can read off is epsilon over the square root of 2 pi e. Okay, just solving this simple first order differential equation. And it's dm by dt is equal to m over something to do with t. So you know it's a power law solution, and I've written it down exactly over here. Now, let's plug that back into my solution. So here's my ansatz. Here's what I just derived on the previous page. And so now I have my full solution, putting those two things together looks like this. Now look, what happens when I take the limit L goes to 0? Or I take the limit T goes to infinity? So let's have a look at the L goes to infinity limit. Sorry, L goes to 0 limit, or T goes to infinity. This term over here either becomes T to the power 1/2 plus alpha. This is actually really kappa T. So as I take T goes to infinity or L goes to 0, that's what this term becomes. And this term is left here, L to the power 2 alpha. So I've got L to the 2 alpha over kappa T to the 1/2 plus alpha. That is my long time behavior, and then it's times e to the minus x squared over 2 kappa T plus L squared. So the point is this: even as I take the limit as T goes to infinity, my solution still remembers the initial condition L. And it needs to have that there for dimensional analysis grounds, because if I have alpha to be non-zero, then I have to have, since my dimensionless parameter is L squared over kappa T, if I have a kappa T to the power alpha, I have to have an L squared to the power alpha by dimensional analysis. And so what's happening here is that the system has remembered its initial condition. So let's recap. For epsilon equal to 0, if I have my diffusing stuff, I measure it at long times. Epsilon equals 0 means I have a conservation law. So if I measure m of t at long times, I can infer the mass of the initial distribution. And I can take the L goes to 0 limit, okay, the system forgets the initial condition after sufficiently long time. So that's what we saw for the regular diffusion equation. Now, when epsilon is non-zero, so this is now the Baron-Blatt equation, now what happens is that the solution at long times looks like this. And at long times, it always depends on the width of the initial condition, however big time is. So what that means is that you cannot infer what was the mass of the initial distribution by just measuring it at late times. So even though I've spent a huge amount of time letting this thing diffuse out from 1 centimeter wide to 100 miles wide, the system never forgets its initial condition. And so the L goes to 0 limit is singular. The system remembers the existence of the initial condition with a non-zero width, And the anomalous dimension that I get, the 2 alpha, alpha was epsilon over the square root of 2 pi e plus higher order terms that you can calculate. So the anomalous dimension depends on epsilon, but it doesn't depend on L. But the reason that you have a non-zero anomalous dimension is because you have, the system has scale interference. The system has spread out in time. It's now 1,000,000 miles wide or 100 miles wide, but it still remembers that at t equals 0, it was at only 1 centimeter wide. So the renormalization that you have in space in statistical mechanics is a renormalization in time in these dynamical systems. Yeah.
Think about it physically what this means, because since M is not in this means that the thinner your initial condition is, the slower it
Can you speak up, please?
in this solution, because M is in the numerator, it means that the thinner your initial condition is, the slower it would diffuse. Whereas in the original diffusion equation, it doesn't depend on M.
Well, what happens is this. If I take the limit L goes to 0, my initial distribution does not go to a delta function. So this cannot go to a delta function. It's going to be a much more singular initial distribution. So it's going to have a huge spike at the origin, a spike much more steep than you would get from taking the L goes to 0 limit of the Gaussian. But yes, it means that it means that the effective mass that you observe depends on what that initial width was. That's right. But the long time behavior scales in time. How it scales in time doesn't depend on that. The actual magnitude does, but how it depends. Okay. Now, wait. I want to just tell you about another physical interpretation. Okay. So this is like space. This is like a renormalization in time. And I'm telling you about how you can observe, whether you can observe the initial mass of the system from late time observation. Now, how many people here have done any class in quantum field theory or read about quantum field theory or anything? One person has. Tiny bit. Okay. What was the problem that Feynman and Gell-Mann and Lowe and others in the 1950s were trying to solve? They were trying to understand what happens to an electron. They were trying to understand what is the physical interpretation of renormalization. So they said, well, I've got an electron, and in order to make the theory finite, I have to have wave function renormalization and mass renormalization and charge renormalization of the electron. And why is that? Well, because the idea is if I've got an electron over here, so here's my electron, it creates a little, vacuum polarization around it. And so if I'm a long distance away from the electron and I take a measurement of its charge, I will see a certain charge. But if I go closer in to the electron and sit, say, very close to it, I will see a different charge, because these charges here, the vacuum particle-antiparticle pairs, what they do is they screen the charge on the electron. As I get closer and closer to the electron, the charge that I will see will be different from the charge that you see in a physics textbook. We measure it a long distance away, and we see the effect of the charge of the electron, its original charge, plus the screening cloud of virtual quantum particles around the electron. And so this was the problem in quantum electrodynamics that Gell-Mann and Lowe set out to solve in the early 1950s, and Peterman and Stuckelberg as well. They wanted to understand the short distance behavior of quantum electrodynamics as I get close to an electron. So you have the idea that it's not, remember that the coupling constants scale with space, That's what Kazanov taught us. Well, here the coupling constants are the coupling constants in Coulomb's law, the charge on the electron. The coupling constants there, they change with space. As I get closer and closer to the electron, what I start to see is, the electron, the vacuum polarization, that's all behind me. And I just see fewer things in front of me. And so I see a different amount of charge, effectively charge on the electron. So the charge on the electron, you a long distance away, from the electron, you can't observe the bare charge on the electron, the charge that it actually has at small distances. It's unobservable. In the normalization in time, you can't observe the mass of the initial distribution because you only look at it at some finite time and it gets renormalized through these processes that I've described. So the renormalization in space, in quantum field theory, or in Stant-Mech is a renormalization in time in these partial differential equations. Okay, all right, you had a question. Is it a good question?
That's a good question. So I don't know. So the boundaries for the initial kind of like condition, that's kind of like it's memorized. Is that the
Which boundary?
The diffusion coefficient, that kind of boundary.
Do you mean the boundary? Do you mean this boundary?
Yeah.
So that boundary diffuses, and in doing this little calculation that I just did for you, this heuristic calculation, I just said, well, epsilon is going to be small, so we will just use the epsilon equals 0 solution for this boundary. This boundary is where dx squared u is equal to 0, and so I know how fast that boundary moves. I can solve it from the epsilon equals 0 solution of the diffusion equation, and that's how I know it's time dependent. But it does get changed, but it gets changed by amount of order epsilon, and then that just changes the anomalous dimensions to order epsilon squared. Okay, so what I've just shown you is a heuristic calculation, and now I'm going to show you a formal calculation which is precise, that doesn't make these assumptions. So did I answer your question? Yeah? Okay, all right. Okay, so this is what you learned in class last week, so I'm going to skip this page. This is just like what happens in Stant-Mech. We talked about quantum field theory and the charge on the electron. Here I'm talking about the 2-point correlation function. Scaling is k to the minus 2 plus eta. We know by dimensions it has to go to L squared, and so there has to be the lattice spacing coming in, and so the system remembers the existence of the lattice. So this renormalization in time that we're seeing in the differential equation is exactly the same as the renormalization in space that you see in Stant-Mech, and there's normalization in space that you see in quantum electrodynamics. Okay, how do you solve this problem correctly? Okay, so that was the heuristic calculation. So now I'm going to sketch for you a way to solve this using perturbation theory. So this, what I'm going to show you is basically exactly what you do in quantum electrodynamics to solve renormalization in quantum field theory. But here we're just doing it for a differential equation. There's no Feynman diagrams. There's no, well, there are actually, but you don't. Well, I don't need to show you them, and you don't. And there's no gauge invariance and all of that stuff. So I'm going to just go through the solution. So what you do is you take the Baron-Blatt's equation, and I'm going to write it like this. So let's have a look at this first line here. Okay, so the diffusion, so I've written it so that it writes like this. On the left-hand side is the diffusion equation operator. And then on the right-hand side, if epsilon was equal to 0, I would have nothing. But what happens here is that we have the diffusion, when epsilon equals 0, then I just have a, then this equation is just satisfied. So I've just got my kappa sitting in here. But when epsilon is non-zero, then when this Heaviside function is positive, then my diffusion coefficient changes by an amount dx squared u, and I've written that dx squared u term as an inhomogeneous term on the right-hand side. Now, why have I written it like this? I've written it like this because I know how to invert the diffusion equation operator. I know the Green's function for the diffusion equation. So I can write down an integral equation solution to this equation and then expand that integral equation solution and then get a perturbative solution to this equation. So this is, in field theory, this would be called like the Schwinger-Dyson equations, for example. So what you do is you find the Green's function for your various wave functions and fields and things like this, and then they're nonlinear equations, and you solve them by perturbation theory, which means solving an integral equation by an expansion. So here is the solution. So all you do is you're basically writing down as u is u naught plus epsilon u1 plus epsilon squared u2, so on and so forth. You stuff that into the equation, you work out what the solution is order by order in perturbation theory. So this is your perturbation theory. Okay, so I'm not going to do that for you, but here's the answer. So here's what you get. So the first term is just this one over here. This says start off with your initial condition. Confusingly, I've used y as my time variable, so I apologize about that. You start off with your initial condition, that's this initial condition over here, and then solve it forward in time using the Green's function of the diffusion equation, that's g, and that gives me the solution of the equation. So that's what you would do if you were just solving the diffusion equation, solving it by Green's functions. But now we've got this extra term. So we've got this extra term on the right-hand side. So when I take this equation, multiply through by the Green's function of the diffusion operator. So remember, d by dt minus kappa over 2 dx squared acting on g is equal to delta of x minus x prime, delta of t minus t prime. So that's what I mean by the Green's function. Then I have an extra term, and that extra term is this one over here. Okay, so I've got u, which is what I want to find on the left-hand side, and it's also here on the right-hand side. So this is and it's also here as well. So it is horribly nonlinear. Okay, so now what we're going to do is I'm going to do a step that I'm not going to show you the algebra, but it's in chapter 10 in my book. So you can evaluate these integrals asymptotically as t over L squared goes to infinity, and the solution looks like this. So this is asymptotics, and you have to be fairly careful in how you do this, and that's in my book and in my papers. And this is the solution that you get. So U starts off as looking like the solution to the regular diffusion equation, m naught over 2 pi square root of 2 pi kappa t times e to the minus x squared over 2 kappa t. That's the solution of the diffusion equation with the initial mass. But it turns out that there's another term. The next term that comes in when you do the calculation is you get this term over here. And you can see that this term over here, as t over L squared goes to infinity, meaning L goes to 0 or time goes to infinity, this has a logarithmic divergence. And the logarithmic divergence is not the whole solution. It's just a logarithmic divergence of a term in the perturbation theory. This is exactly the problem that Feynman, Tominaga, and Schwinger solved when they developed renormalization theory and got the Nobel Prize for that. The whole problem of quantum electrodynamics, you can write down quantum electrodynamics, people knew how to do that from the 1930s, but every time you tried to calculate anything, you got infinities. And as you know, the problem of what renormalization does, it's some magic hocus pocus procedure that turns infinities into non-infinities. And it's just some magic, and nobody really understood it at the time, including Feynman. They didn't really understand what they were doing. But this is the way it manifests in quantum electrodynamics is a logarithmic divergence in space. Here we have a logarithmic divergence in time. Okay, so now how do we solve this? We're going to solve this the same way that people did, like Feynman, Tomahawk, and Schwinger did in quantum electrodynamics. So we're going to do perturbative renormalization. So the point is this: we know that this mass associated with the initial condition is not observable at late times, just like the charge isn't. So what people said was, okay, where we thought we had the bare charge of the electron, the original charge, actually what we're seeing is some renormalized charge. So here we're seeing a renormalized mass. So I'm going to say, well, actually, that mass there shouldn't be m0, it should be some other mass. And that mass will be related by a renormalization constant to the original mass, the mass that it started off with. But it's going to be a mass that has some dependence on L, because we know that the mass does. And if it depends on L, since the mass, since a Z, this quantity here, this renormalization constant has to be dimensionless. If it depends on this variable L here, then it has to depend on another length scale, and there's no other length scale in the problem. So you say, okay, well, let's just make one up. Okay, we'll make up the length scale, which is our unit of length. It could be a foot, it could be a light year, it could be anything you want. So we make an arbitrary length scale, which is put in here. There has to be a unit of length, doesn't matter what it is. So that has to go in there, and it's necessary to have that in there because Z has to be dimensionless. So this process that we're doing now is we're going to replace what we thought was the initial mass of the distribution by something that has changed. The thing that has changed is still a mass, so it has the same units, but now it depends upon L or it depends upon time. And so this process of renormalization introduces a new length scale. Okay, now what is this renormalization coefficient? Well, we don't know, but it's going to depend on epsilon, and so we're going to do a power series expansion of that coefficient. If we're going to do a power series expansion of that coefficient, they're going to be coefficients, an as a coefficient of epsilon. Since the renormalization constant depends on L, and it depends on the arbitrary scale mu that we've introduced, then the expansion has to look like this. And what we're going to do, what the renormalization procedure does in field theory, says go through order by order in perturbation theory and cancel out the divergences that you see. So we are going to make the divergences in the perturbation theory go poof away. Okay, how are we going to do that? Well, we're going to choose these coefficients A1 to make them go away. So here's how I'm going to do it. I'm going to choose A1 to look like this. 1 over the square root of 2 pi e times the logarithm of some arbitrary constant times mu squared over L squared. Okay, it depends on epsilon, it depends on mu squared over L squared. I'm going to choose it to be this. Okay, why do I choose it to be this? Take that form for A1, take this form, so Z is now equal to 1 plus A1 times epsilon, and plug that into this formula over here. So here's the result. U is M. So this M is now the actual mass, which I don't know what it is, the renormalized mass, times e to the minus x squared over 2t, 1 plus epsilon over the square root of 2 pi e log c1 mu squared over L squared plus order epsilon squared. That is my Z factor. That's my Z factor that comes in from here. Okay, so that's what I've done. And then I've got my divergent perturbation theory, which has this term here with this unpleasant logarithmic divergence. Now, okay, why did I choose this magic term? If I take this square bracket and multiply it by this square bracket, let's multiply them out, I get 1 minus epsilon over the square root of 2 pi e, and then I get the next term is logarithm of t over L squared, that comes from here, and I get the logarithm of L squared C1 over mu squared, which comes from here. And you can see that the L's cancel. Okay, so the L has cancelled. So all of my problem, remember, so L cancelled. Okay, why is this great? Well, the divergence is when t is equal to is a fixed number and L goes to 0. Here's my logarithmic divergence. You can see over here. I've obscured it with this. Let's get rid of that. Okay, there's my t over L squared. Keep t fixed, send L to 0. I get a logarithmic divergence of the log of L squared. Well, I've just cancelled out L squared. So what happens to the terms that I kept when I send L goes to 0? Nothing, because L isn't even there anymore. Okay, that's the renormalization process. I've turned an infinity into something finite, at least to this order in epsilon. If I went to order epsilon squared, I would still have some L's, and I'd have to do this procedure to higher orders in epsilon and so on. And you can show that you can do this to arbitrary high order, and it will work. So now I've got my solution, which is now finite. So now the whole point about this is I've now turned my perturbation theory into something that is finite. And we like things that are finite. There's only one problem. What's the problem? I don't know what M is, and why don't I know what M is? Well, I don't know what M is, but there's an even bigger problem than that. I've managed to get rid of L, and so my solution doesn't diverge when L goes to 0. But still, I'm unhappy with my solution. Why? It depends on mu. It depends on mu. To do this magical trick, I had to have L squared in my formula for A1. Because A1 has a logarithm in it, I can't have logarithm of L squared. I have to have another length scale to make that argument of the logarithm dimensionless. So I had to introduce an arbitrary length scale to do this renormalization. So it's mu. Okay, what is mu? The answer is it doesn't matter. Who cares? Okay, the answer can't depend on mu. So I should have that if I take my solution for u, this is my formula for u, du by d mu should be 0. U must be independent of mu. So if I take this solution and differentiate it with respect to mu and set it equal to 0, what I find is that I get an equation for m, that m scales like this, and so therefore m of mu of any scale mu is m of sigma to some scale sigma over mu to that. So this is the solution of that differential equation. Du by d mu is equal to 0. That's called the renormalization group equation. And this equation here, you can see, this looks very much like the equation I had in my heuristic derivation of this, where we figured out how does m scale in time, and we found that m scales in time as dm over m is equal to dt over t times some prefactor. It's the same, it's actually the same equation. Okay, so what I've just told you is that the solution looks actually like this. So u is m of mu, there's m of mu, and there's mu here. So in order for the solution to not depend on the scale mu, m of mu has to have this magical form. If m of mu has this magical form, then now my solution looks like this. And what we've discovered is that at least to this order in epsilon, if I take du, differentiate it with respect to mu, the dependence of mu here and the dependence of mu here cancel out to this order in epsilon. Okay, so it doesn't matter what I choose mu to be. Okay, so I'm going to choose mu to be this. Nothing to stop me choosing mu to be that. And if I choose mu to be that, then what I end up with is my final solution, which looks like this. And now I get this extra factor of t scaling as to the half plus alpha, where alpha is epsilon over square root of 2 pi e, plus higher order corrections. So this is what renormalization is. This is the renormalization that you will learn if you take a quantum field theory course, but this is now just done for a regular differential equation. Okay, so I'm going to skip those. We don't need that. So I think that's where I'm going to stop. So what is the conclusion? That there's more here, and these are in the notes. But basically, this is already the bottom line. Oh, here let's do one more step. Let's apply the initial conditions, and so the initial conditions, we keep the factors of L, and so we end up with this final solution like this. Okay, the initial condition had a width L and an initial mass M. So here is my final solution, and you can see that as advertised, I have this singular dependence on L raised to this power epsilon over the square root of 2 pi e times the regular solution over here, and this is the thing that allows the solution to have an anomalous scaling in time. So we've got from this calculation exactly what we had done before with our heuristic calculation from half an hour ago. So the heuristic calculation was pretty good. It actually was the order epsilon calculation, the order epsilon result from a very systematic way of solving this problem by doing renormalized perturbation theory. Okay. Any questions? Yes.
So I'm a little bit confused about like the difference between the renormalization of the space and the renormalization of time.
Yep.
In the space, like renormalization, we can think about like coarse graining.
Yes.
But how does like apply here?
Right. Great question. So the question was, in space, we know what renormalization is. We think about coarse graining, blah, 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 all the things that we've been doing this course. How do we do this in time? Okay. So the analog of that in time is the following. And you can, and in my book, in the chapter 10, I show you the Wilson version of renormalization. This is the Gelman-Low version. So what you do is this: you take your solution, you evolve it forward in time a little bit, then you stop, then you rescale everything, get it back to its initial condition, then you start again. So it's like this: you've got a solution that is evolving in time. So it starts off like this. You evolve it forward in time a little bit, so it goes like this. Okay, so this is t equals 0. This is t equals, let's say, t1. Okay, so that's the first thing. Then what you do is you rescale the axes. So you can say, well, why don't we just do this? Why don't we rescale y, which is u, of course. This is the function u. Rescale x. And then this solution then now will become something like that, close to the initial, to the original one. Then do it again and again and again. And what will happen is that eventually this solution, the fixed point function that you see on your computer screen as you start with your initial condition, it evolves, it goes down and spreads out. You rescale the axes back up here. Eventually, your computer screen, you'll see the thing wiggling around like this. Eventually, at long times, it'll stop evolving. Under this process, it will just stay fixed on the computer screen as the axes in the y and x directions are being rescaled. You've reached a fixed point. And so this is the Wilson version of that. So coarse graining in space means you evolve in space a little bit and then you rescale. Renormalization in time, you evolve in time a little bit, rescale, and then you have an iterative map. Then you iterate this map over and over again, and eventually you get a fixed point. But here it's not a fixed point of like 2 or 3 variables like the coupling constant J and H, say, in the Ising model. Here you have an infinite number of variables because the variables that are renormalizing are the actual function itself. U is a function of X at every point in space. So U, the function that is evolving, is behaving like the coupling constants. It's just it's an uncountable infinity of coupling constants that are being renormalized in this. This is called a functional renormalization group. Does that answer your question?
Yeah.
I'm glad you asked the question because I was about to explain that, but now it comes into a question. Okay, it's amazingly cool that this happens, and the great thing is that that was just one problem. Okay, so I want to just show you something very very amazing. I'm going to show you. Here's an equation. Okay, at the top of the page. Can you see this horrible nonlinear equation? This is a toy model of the Navier-Stokes equations for the flow around a sphere. Okay, it's a toy model of it. Okay, if you tried to solve this problem, I guarantee you would not be able to solve it. It is horrific. When I was a student at Cambridge, one of the lecturers, he was an excellent lecturer. He gave a whole class on perturbation theory and asymptotics. This problem was like the last one in the class, and it was called the terrible problem because it's so difficult. Okay, when you solve this you can solve this by renormalization group, and you find a solution in terms of these elliptic functions or these weird integral functions that you can see here. What I wanted to show you something amazing. Yeah, here is the solution of that equation. This horrible equation. What I'm showing you here are different solutions. So the black dots are the numerical solutions. The line going through the black dots is the renormalization group result of first order. And then these solutions here, this one and this one, this one and this one, these are results from matched asymptotic expansions, which is something you may have heard about. Asymptotic techniques to solve the problem near r equals 0, and then to solve the problem near r equals infinity. That's how Stokes' sphere problem was solved. This whole theory of matched asymptotic expansions is a sort of foundation of the applied mathematics theory for singular perturbation. Here, the small parameter, epsilon, is very much less than 1. Here, epsilon is of order 1. Okay, so most asymptotic methods work when there's a small parameter and it's really small. Okay, the renormalization group is fantastic because it gives you solutions to the problem which work even when the small parameter is actually order 1. We saw this with the epsilon expansion. We did the epsilon expansion for the Landau theory, and we found that even if I set first order in epsilon and then I set epsilon equal 1, it still gave us a reasonable result. And that robustness of these renormalization group methods, which is due to they're intrinsically non-perturbative. Okay, we didn't just do perturbation theory. We did perturbation theory, and then we used renormalization group conditions in order to improve the perturbation theory. And it is this extra magic that means that the renormalization group magically sums all terms to arbitrary orders in perturbation theory and does something very sophisticated in terms of the analytic structure of the solution to the problem. So this was one of the things that we did, and then the other thing, that was a big selling point of this method was the traditional way to solve asymptotics problems is you have to guess the scale, how things scale, and often you have to guess, that you want a small parameter. So you say that there's a length scale, it's going to scale like epsilon squared or something like this. When you do the calculation, you find, oh heck, there's an emergent length scale which goes like log epsilon or something. Who knew? You'd never know that ahead of time. And so applied mathematicians had to guess these scales using these methods. With the renormalization group, you don't have to do that. Everything is mechanical. Even a physicist can do it and get the right answer. And the renormalization group method tells you about all the non-analyticities that you get in standard methods, and it automatically preserves the symmetries of the underlying equations. Okay, so this is about how to see a black hole in the lab. I'm not going to show you that. Well, you actually can. Here. This is a fluid mechanical analog of the space-time near the onset of a black hole formation. Yeah. Do you want me to tell you about that? Okay, I'll tell you, but it's very superficial. If you look at viscous flow in a wedge, what you find is that depending on the angle of the wedge, this was discovered by Keith Moffat in the I don't know in 1966 or something like that. Okay, mathematically, you solve the low Reynolds number. There's nothing to do with turbulence. Low Reynolds number, Navier-Stokes equations in a wedge, right? What you find is that you'd say, if I've got a flow going like this, you'd think that the flow in here would be going in and out like that. But it's not. You get these vortices that are like this. And you can see them here, these vortices rotating in this flow visualization. Okay. You would think that the flow would just be some regular flow like I've sketched in brown on the picture. And that would be scale invariant, like the scale invariance of the diffusion equation or the Baumgarten equation that we've been talking about. This picture turns out to have discrete scale invariance. It's not continuous scale invariance, it's discrete scale invariance. It's a completely different thing. You can't just scale just by an arbitrary amount in space and time and get the solutions. You have to scale by discrete jumps, and what those are precisely determined, and then the solutions map onto each other. So it's a different symmetry of the underlying differential equations. So this is what happens in this flow here. As I change the angle of this wedge, eventually what happens is these vortices go away. If the angle of the wedge was very big like this, the flow would just be going in and out like this, just like you would expect. But when the wedge gets very, very narrow, then you get these vortices. And so so remember Feynman was saying at the beginning, we need a way to visualize, to understand the qualitative content of equation. What are the emergent states that come out of, say, the equations of fluid mechanics? Here you go. I've got a wedge. It's angled like this. What's going to be the flow? Well, you're going to say it's going to be just a regular flow going through the wedge. Nope. It can actually, as you change the angle, there's literally a phase transition to a state that looks like this with broken scale invariance, discrete scale invariance. It's fantastic. And the same thing happens if you have a scalar field collapsing to form a black hole in general relativity. The space-time also has this discrete scale invariance. So anyway, all of these things are basically similarity solutions with anomalous exponents, but the anomalous exponents are complex. Complex critical exponents, and that's what gives you this discrete scale invariance. Anyway, there's a whole lot to see there. There's a whole lot to do. So here are some of these. Here are some of the papers. Well, these are some of the papers that I just mentioned here. There's hundreds of others. Okay, that's the end of the course. So I hope you found it interesting. I hope you could see that this tiny problem of looking at what happens right near a phase transition, which you'd say nobody should care about. Hopefully I've shown you that actually that problem, thinking about that really changes the way you view all of physics, and not just phase transition problems in statistical mechanics, but even well beyond that. So I hope you enjoyed the course. I look forward to hearing your term essays next week when we'll meet here and you'll give your lectures. So thanks very much. All right, let's turn off Zoom.